Many of you know how to take derivative of a function once or twice, but have you ever heard of taking a half derivative or a third derivative of a function? Believe it or not, the concept of taking fractional derivative has been around for more than a century, and it has many applications in mathematics, physics, and engineering. Now, what is fractional derivative? There are different definitions for fractional derivative. Some of them are equivalent. In this video, we are going to visualize this concept in a new way, which should be accessible to a good high school student. If you want to look at alternative definitions or you want to read more, look at the Wikipedia page on fractional calculus. To start, say we are given a function f of x, and we want to go after its fractional derivative. The first thing we want to do is to express such function in terms of its Fourier coefficients. The basic idea is that almost any function can be expressed uniquely as a sum of sines and cosines with different frequencies. Let's look at an example. We say that we have a function f of x, and for this function we can express that function as a sum of trig functions, cosine and sine. In our example, f of x is 1 times cosine of x plus 1/6 cosine of 8x plus 1 over 2 times sine of 3x. And altogether I have this interesting graph of f of x. The point is that if you want to give me a function, instead you can give me the coefficients or numbers appearing in front of cosine of kx and sine of kx for all positive integers k. These coefficients are called the Fourier coefficients, and we are going to use them to define our version of fractional derivative. There is an overall constant term a0 that we are going to ignore in this video. Let us now visualize function using these coefficients. Let us draw a coordinate plane. We would like to use the term cosine axis for the horizontal axis in the plane, and likewise sine axis for the vertical one. Okay, now we want to add a red point to this plane. Say at 1.5 and 0.5. Our point now represents the function f of x equals 1.5 cosine of x plus 0.5 sine of x. Just like that, we can go ahead and add a second point in blue. The second point is associated with the frequency k equal to 2. Red and blue points now together represent a function f of x equals 1.5 cosine of x plus 0.5 sine of x plus 1 cosine of 2x plus 1 sine of 2x. So you can just imagine adding more colors, more points with new colors that represent higher frequencies, like k equal to 3, k equal to 4, k equal to 5. So a sequence of points in cosine sine plane can represent a function in terms of its all Fourier coefficients. Now, what these have to do with derivative? Let us take a red point as example, which represent the function cosine of x, and there is no sine component, and we want to apply one derivative to this. All you know, we get sine of x. The derivative of cosine is sine and is now the point 0, 1. What happens if we take another derivative? Derivative of sine is equal to negative cosine of x. Now, visually, it's clear. Every time that we apply one derivative, we end up rotating the red point by pi over 2, or 90 degrees. Derivative of cosine is sine, and if derivative of sine is negative cosine. Now, you can pause the video and try to guess what half of a derivative can possibly mean. The picture tells you if you want a half derivative, you can just simply rotate the red point by pi over 4 instead of pi over 2. But even more, it doesn't have to be 1/2 of a derivative. You can have arbitrary continuous choice number of times you want to take derivative of f. For the points with higher frequencies, like the blue point, the same principle applies except with an additional scaling. Remember, the derivative of cosine of kx is k times sine of kx. This simply means that if you want to apply a derivative to a point with frequency k, we rotate the point by a times pi over 2 and scale it by k to the a. Okay, here's now how to apply any number of derivatives to a function f of x. Represent the function on the cosine sine plane as a sequence of points, one for each frequency. Here we only have 3 frequencies, but in general you might have many. You then rotate all the points in the plane by a times pi over 2 and scale them according to their associated frequency by k to the a. At the end, you have your fractional derivative expressed in terms of sine and cosines. Thank you for watching the video and have a good day.